Right, in this lesson we're looking at Einstein's theory, because there's some interesting things that sort of come about from this frame of reference stuff. So if inertial, need to write it properly, inertial frames of reference remember, they can be one or two things: rest or constant velocity. Right, so they can't be accelerating. So if that's the case, and so all inertial frames of reference, physics laws hold. All right, so if that's the case, then looking at this particular diagram in this example. All right, so here we've got an example. So in part A, over here, the observer and the boy dropping the basketball are in the same box, if you like, and so what happens is the observer quite rightly sees the basketball fall to the ground. Now, what we're saying about inertial frames of reference is that if we then change that particular thing so that the observer and the boy are now in their box, but they're moving together at 100 metres per second, then the boy drops the ball and the ball hits, and so really the observer and the boy, they really have, if this box is closed and all that, then they really have no indication or anything of whether these two are different. I mean, for us standing outside the box, yeah, we can see that the one in B is moving, but if we were actually in the box and the box was moving, we wouldn't actually, we'd just be standing there, and that's just like being in a lift. Okay, so you're in a lift, yes, certainly feel a start and a stop, but when it's moving, after it's started and stopped, makes no difference as to whether, when it's moving at its constant speed, makes no difference whether it is or it isn't. So in terms of the ball dropping, then it's exactly the same. So what we can do that is we can say, okay, well, how is that different to, say, this? So now, over here in A, we've now got the observer that's now stopped. The boy and the ball are moving up at 100 metres per second. The boy drops the ball falls down. The observer observes the ball eventually hit the bottom of the box that the ball's in. Now, how is that any different to the one on part B on the left? So now the observer's moving down at 150 metres per second. The boy in the box there, he's moving up at 50 metres per second. So in the frame of reference of the observer, the boy is still moving away from him. So, the velocity of the boy relative to the observer, so velocity of the boy relative to the observer is the velocity of the boy, which is 50 minus, and it's a negative 50, so it's still 100, and when we look at that frame of reference. So as far as the observer is concerned, that boy is still moving up relative to him or her with 100 metres per second. Boy drops the ball. So as far as the observer is concerned here, it makes no difference as to whether they're stopped or whether they're moving, provided the relative velocities are the same. All right, and so the relative velocity of the buoy in the box in both A and B is 100. So from that we can conclude that the frame of reference doesn't affect the observation. All right, and so that then leads us to, and in your notes there, it's called the Galilean Principle of Relativity, which then tells us that the laws of motion or mechanics are the same in all frames of reference. Inertial, not all frames of reference, inertial frames. Alright, so they're all inertial frames. Inertial is important, so remember that's not accelerating. Alright, so that's all sounds good so far. It's all good. We understand that. We can accept that that's okay. So James Maxwell, or James Clerk Maxwell. So Maxwell and the speed of light. Right, so Maxwell came up with some equations back in the 1860s, and he produced four equations four equations that connect electrical and magnetic interactions. All right, so he's got four equations. Now, in those equations, there was a prediction. And that prediction was of the speed of light. And that prediction, in a vacuum, and that prediction was, and we see to it, is that it would be 3 by 10 to the 8 metres per second would be the speed of light. Alright, so that was his prediction. Now, at the time, it was thought that electromagnetic waves needed something to travel through, so Maxwell created this thing called ether. Einstein later determined that was not necessarily the ether, that wouldn't matter. Now, there was an issue, and that issue was that Maxwell's prediction that the speed of light is the same for all observers. Alright, and so that seems a bit strange, because that would mean then, if you are standing here having a look at this light, and say you've got this one bit of light here that's moving towards you, and the source is moving towards you, so you get this light coming, and then you've got another light source that's moving away, and you've got light coming towards you. From what we've said before about the relative velocities, and that you would expect that the velocities would be different. And that's where the issue is. So, is the same speed. So that was the prediction from his equations, that you would actually see it as the same speed. So the prediction says yes. All right. So that seems to be a bit of a contradiction, and we'll get to that in a minute. And so then you notice the two important aspects arising from Maxwell's equation: the speed of light, 3 by 10 to the 8, and the other thing is the same for all observers. So that seems to be a bit strange. So this is where our old mate Einstein comes in. All right. So in his theory of relativity, so he did this in 1905. So his two postulates, there was two postulates, and we've already talked about these two postulates, but I'll just write them anyway. So laws of physics are the same in inertial frames of reference. And the other one was speed of light, same for all. All right. So, as I said, it seems to be some contradictions there. So, an example of that is here in this one. So, if we've got a rocket ship, space shuttle moving towards a star at velocity v, and the light's coming out of the star at speed c, and so Einstein's saying that even though this space shuttle's moving towards, they still measure the speed of light as the same, so 3 by 10 to the 8. All right, so in your notes, there's a whole bunch of things and words there. So basically what Einstein did is then he questioned and proposed. So we've got space, which is in time. And what Einstein said is that they're not absolute. So what does that mean? That means things like length, mass, and time were not absolute, so could change, which seems to be pretty strange, pretty interesting. So again, a Gedanken experiment, a Gedanken train that we've got. So Einstein's Gedanken train, there's his Gedanken train right there. So we've got these two people, Amaya is this person, and then we've got Bin, and Bin is this person. So and then we've got some light being gone from C both sides. The train's moving forward, and as Amaya and Bin, when they both look at that, they'll both see the light, and they'll see the light hit the front and the back wall at the same time. Because as far as they're concerned, in their frame of reference, because they're moving with their frame of reference that's moving, so from their point of view, the light travels with C both ways. So Amaya and Bin see the light ends at the same time. Now you'll notice there's someone sitting by the tracks down there, and that's Claire. And here's Claire. We'll take the May and bin out and we'll just look at Claire. So if we like, what we've got here is, I'll try and get this, so we've got the train starts here. And so there's the light, that's there. And Claire sees all of that moving, so that a little bit later on, what Claire sees is that the train has moved a bit in a little bit of time, and so has the light. So what Claire is actually seeing, and so when that's happened, this rear wall of the train has moved from there to there, got closer to that light, and this other end has moved away. So Claire, in Claire's point of view, from her frame of reference, she should be seeing the light hit the back wall before the front. Alright, and that kind of makes sense because the back wall's moving towards the light and the front wall's moving away from the light. The rays that went out. But it's different to the other two people. So this is where we get to simultaneous events. So it seems silly that in one frame of reference, so Amaya and Bin, it's simultaneous, but for Claire it's not. So how can we actually get that straight in our head? This is kind of a bit weird. And what Einstein did is Einstein said that space and time are interrelated. So what does that mean? Well, what that means is that there's some sort of four-dimensional relationship. And so 4D. And so what we have is the 3D of space plus the 1D of time. And so what Einstein's saying is that space and time weren't separate, but they were joined together in a thing called Spacetime. And that's really the crux of special relativity, is this thing called space-time. Alright, so, and that then leads us to some pretty freaky stuff. Alright, so I've got three examples here that we'll go through. First one is explain why Maxwell's predictions appeared to contradict the principle of relativity. Well, basically, it's the ether is the issue. All right, because Maxwell actually said that that's what the light travels through. Alright, the ether. And if that's the case, then we should be able to measure the speed of the ether. And according to the principle of relativity, there's no preferred frame of reference, and so this idea that there's an ether that we can measure the speed of light in relative to me, and then therefore we should be able to measure the speed of the ether, then that's where there seems to be a contradiction. All right, and Einstein actually showed that there's actually no need for an ether. All right. All right, the next question. All right, this question's so Maxwell proved that light travelled that speed, 3 by 10 to the 8. And so physicists had some concerns about that. So which one or more statements below outlines one of these concerns? So A, all waves propagate in a medium but there's no medium in empty space. Unlike the speed of other waves, experiments showed the speed of light did not depend on the observer or the source of light. If light was a wave, it would not diffract, and the speed of light predicted with Maxwell did not agree with the measured speed. Right, so let's work through these, and I'm going to work through a couple of ones. First of all, so the speed of light predicted by Maxwell and the measured speed were the same, so that was out. If light was a wave, it would not diffract. Well, waves do diffract, so that one was out. And the question says one or more. All waves propagate in a medium, but there was no medium in empty space. So that was a concern, all right? And so that's where Maxwell created the ether. All right, so no meter. So he created this ether, said, yeah, there's this ether there. So that's all right. Unlike the speed of other waves, experiments showed the speed of light did not. And so the speed of light did not depend on the speed of the observer or the source. So that was the thing that was concerning. Because that relative speed, different frames of reference, whether it's moving, depending on your frame of reference you're moving in. So A and B are both the things that are concerned. All right, and then the next example. Here we've got the next question, example 13. So a space station is emitting light from lasers fixed to it. So here's our space station in the middle here. And Nilofer and Haiti are situated on 2 planets, and the planets are at rest relative to each other. And they measure the speed of light from the space station. Haiti, which is Hattie, this person here is moving towards the space station, and the other, Nilofer, in orange here, is moving away from the space station. And the speed of light is c. So which one of the statements A to D below gives the correct values for the velocity of light measured by Nifola and Hattie? So velocity of light measured by Nifola and Hattie. Now remembering, don't be confused, what one of the postulates there was for this special relativity stuff, and also predicted by Maxwell, is that the speed of light is the same for all observers. Right. So if it's the same for all observers, it's got to be C for everyone. So when we look at A says they both measure it as C, so A is the correct answer. All right. Right, so this is some pretty interesting stuff, and some stuff that really challenges our thinking and the way we think and what we've learned so far about physics and things. So we will, anything you need clarifying, make sure you ask, make sure you have a look at the videos and things that are relevant, and then if there's some text questions and then a couple of questions in your notes.